here to introduce our new map, which has been delivered from the printer. I've never seen it, at least not in this form, courtesy of Gold Candle Taxi from a local printer. And I'm going to talk a little bit about that in the middle of my talk, but I will encourage everyone to come up and have a look at it, because a lot of what we've done in Metal Oceans was stimulated by a single little map that was created by a group of us, but led by Meg Stewart. That's down in the corner of this new map. And the rest of the map is about 5,000 kilometers of the Indo-Australian margin. And based on how much Meg's map, we call it Meg's map, how much Meg's map stimulated in terms of discussion and so forth, all the way back to the Abitibi, I'm hopeful that this new map will do the same. A lot of what has been described in the early part of Metal Oceans is articulated in a paper that just came out in Economic Geology on our, what we call our microplates model. And Keaton has referred to it earlier, and I'll describe that a little bit now. And it really sets the stage for why we bothered to create this much, much larger map. So Keaton was focusing on volcanic complexes, very local, 50, 100 kilometers max. Microplates are much larger than that, but also influence a huge amount of metal endowment. The idea behind the microplate story is simple, and that is that in order to account for a heat loss in the Archean Earth, we probably had many more, much smaller plates. And this is manifested, for example, by a modern day microplate mosaic, which exists in the, along the Indo-Australian margin, viewed here in an Antarctic polar projection. It gives you a really nice image of what a microplate mosaic might have looked like in a hot Archean. And the heat is efficiently extracted, of course, from these microplate mosaics by hydrothermal activity, which is shown by the red dots. These are modern day black smoker deposits that basically festoon the plate boundaries around the microplates. The idea being that the more plates you have, the more plate boundaries you have, the more mineral deposits form. And it turns out that this looks like it's happening at all scales. It's infinitely scalable from the planet all the way down to the Northern Lau Basin or the Abitibi Greenstone Belt. What were some of the main observations of the microplate model that are described in this paper, which, by the way, is open access? You can download it from the November issue, are listed here. So essentially, the microplate model means more numerous and smaller plates that result in a greater total ridge length. So if you go back to the Archean and take one of Bleeker's puzzle models of 35 plates, if you unfolded those 35 plates, you'd have about 500,000 kilometers of ridge length compared to 60,000 kilometers that we have today. So more numerous plates mean a greater ridge length, which means more extraction of heat. And we refer to this as the many short, slow spreading centers versus one long, fast spreading centers. The microplate formation also leads to a reduction in spreading rates. So the more spreading centers you have, the slower they have to move in order to create the crust that's being created. And this slowness might explain the longevity of some Archean assemblages. The way that the plates grow is analogous to autochthonous growth, which is what we've heard about earlier, yesterday, I guess it was, which is, consistent with an environment where subduction zone processes were either absent or were in their infancy or were going full steam. Take your pick, doesn't matter, microplates don't care. There's an abundance of crustal scale faulting that occurs in a microplate mosaic as a result of the requirement to accommodate that growth. And Keaton referred to the Peggy Ridge leaky transform, and I'll mention that as well in a moment. And most importantly, down at the bottom here is, from an endowment point of view, the VMS are really confined to narrow stratigraphic intervals. And we attribute that to the sudden release or the sudden creation of melt and fluid pathways. Phil Thurston had a different idea. He had the idea that you had major time breaks represented by sedimentary interface units, and you needed all that time to create the banded iron formations in the VMS deposits. We're looking at it from the other perspective, whereby the accumulation of volcanic piles was rather slow, and the formation of the mineral deposits was rather fast. So almost exactly the opposite of what Phil had in mind, and maybe we can talk about that later. So you've seen this slide 3 times now, which is pretty interesting because I think we all decided to show it independently. And it is basically where Keaton is heading with the characterization of volcanic complexes within the Abitibi Greenstone Belt that have, as he clearly pointed out, have very great similarities to what's going on in the modern ocean at the same scale. So in our synthesis paper, which is underway and almost done, we're revisiting some of these central volcanic complexes in the Abitibi. What are they? They're a mix of, as Keaton pointed out, of triple junctions, oceanic rifts, back arc spreading centers, you name it. And if you connect them up, they stitch the microplates. And I think that's the main message, at least from my point of view, is where do these microplates come from and how are the boundaries evolving? Well, they probably start out as nodes of volcanism and magmatism that are connected by spreading centers that ultimately intersect. What are those volcanic complexes? What do they look like in comparison to modern systems? And a much more simplified comparison shown here is that we basically have 3 types of central volcanic complexes that are well represented in the Lau Basin. They are these plume-influenced oceanic rifts, so basically mature back arc spreading centers that have a strong plume influence. That's one category, which might include, for example, analogs to Kidd Monroe or Monroe Township or Chibougamau. We have arc to back arc transitions, so these are localities where you have the transition from tholeiitic to calc-alkaline magmatism, which are probably analogous to something like Selbet, Jetel, Normatel, and Noranda. And then, of course, we have the intra-arc rifts, which have a greater abundance of calc-alkaline volcanism altogether, and they look very much like intra-arc rifts we can put our finger on this map. So that's the background for the synthesis paper. That's not what I'm here to talk about. I'm here to talk about our next steps, which is the creation of this map. And what we're really trying to do, or what I guess I'm trying to do, is to understand how these microplates come together at the sub-province and the province scale. And this is something we've been doing. This is our domain that we've been looking at all along, which is the northern border of the Indo-Australian margin. One of the challenges has always been, where is the boundary between the Indo-Australian plate and the Pacific plate? And it's almost impossible to put your finger on it because of this. It's festooned with at least 30 microplates all the way from New Zealand all the way up to the Solomons. So that's almost the size of the Canadian Shield. There are at least 30 major microplates that are constantly in motion. They're constantly being rotated, and the rotation produces transtension, and the transtension produces spreading, and the spreading produces more microplates. So it's very difficult to put your finger on the boundary between the Pacific and the Indo-Australian plate. Of course, the watershed for us was these maps. And we published our first map in Geosphere. That was so-called MEG's map of the northern part of the Lau Basin. We have another one on easternmost Papua New Guinea. These are the 2 maps that are at the ends of our new big map, and the maps in the middle. What these geological maps allow us to do is calculate crustal growth in the same way that Tauth's documented it for some of the assemblages in the Abitibi. And the simplest observation is that in the case of the Lau Basin, we've divided it up into a northern portion and a southern portion. They're about roughly the same area, but the northern portion of the Lau Basin has crustal accretion rates that are about 3 to 4 times higher than in the southern Lau Basin for terrain that's roughly the same size. And that's simply a function of all the microplates that comprise the upper part of the northern Lau Basin. The structures are unbelievably complicated. Not only is the boundary between the Pacific plate and the Indo-Australian plate pockmarked or festooned with all these microplates, but there are all kinds of other structures that are influencing, in particular, what's going on within the back arc basin. So, for example, this is vertical gravity gradient data that shows, for example, seamount chains. It shows fossil spreading centers. It shows an ancient tear in the Pacific slab. All of that is influencing, I'm not going to use the word subduction at the moment, but all of that is influencing the architecture and the evolution of the back arc basin. Some of the structures that evolve, I've shown that we've all talked about this before, include these very large-scale transcurrent fault zones. This is the Peggy Ridge Fault that Keaton referred to. It accommodates about 600 kilometers of opening of the Lau Basin. So it's a very early synvolcanic transcurrent fault, which is magmatically active and accommodates all that opening in the northern part of the Lau Basin. There are other features, such as this ridge transform intersection. This is a transform that has developed at the northern end of the Lau Basin, where the subduction zone and the trench have curved around, and there are these hairpin turns, and that you can see at least 7 of them on that map, these hairpin turns, which result in tearing of the Pacific slab. And it's the tearing of the slab that allows mantle material, in this case from Samoa, to migrate into the back arc basin and influence the composition of virtually all the volcanic rocks within the northern part of the Lau Basin. That was described in part by Chris and also by Mark Fassbender in this cartoon, which shows there's the hairpin turn in the ridge transform intersection, and that hairpin turn has opened up this slab this tear in the slab, and mantle material from Samoa is arriving into the back arc region and influencing almost everything: the rifted arcs, the back arc shields, and the plume influence spreading centers. Mark Fassbender did quite a bit of work on the igneous geochemistry throughout the Lau Basin and showed basically that we have just about every rock type you can imagine within a couple of 100 kilometers, and including those several suites that are really very closely matching in the case of felsic volcanics, really very closely matching the chemistry and the compositions of Abitibi rhyolites. This is the more interesting outcome of Mark Fassbender's work, which was a machine learning experiment on mafic volcanic rocks in the northern Lau Basin. So this map shows all of the mafic volcanic rocks in the northern Lau Basin. Through machine learning, he identified a number of target classes of rock types. C1, C2, C3 are ridge hotspot intersections and mid-ocean ridge type spreading centers. Those are these dark green symbols. The C4 class was basically ocean island basalts and interplate volcanoes. These are the purple volcanoes that you see here. C5, C6, these are interoceanic arcs and back arcs, near arc spreading centers. And C7 is a class of intra-arc rifts with chemistry that is to some degree similar to continental margin rifts. The point is, you've got all of this within the space of a couple of 100 kilometers in the northern Lau Basin. And you could think of it, if you look at it correctly, as northern volcanic zone in the Abitibi Greenstone Belt and southern volcanic zone in the Abitibi Greenstone Belt with stuff in between. So we're moving out now, and we're looking at comparisons between other basins. The next basin over on that map and shown here is the North Fiji Basin, and we're developing attributes tables that allow us to compare one setting to another. And in this particular instance, we're looking at features such as the symmetry or the asymmetry of the rift bounding faults. We're looking at the size and the depth of the rift bounding faults. We're looking at the presence or absence of pre-rift intrusions, pre-rift faulted basements, rift propagation, ridge jumps, segmentation, nodal basins, triple junctions, transcrystal shift, blah, blah, blah. They're very different in these two different environments, and this closely matches what we envisage as the relative endowment, with the Lau Basin characterized by at least 80 known high-temperature hydrothermal vent fields, and the whole of the North Fiji Basin, as far as we know it, only 26. So there's very distinct differences just in the very simple mapping attributes. But it's more complicated than that, or at least it's more sophisticated than that. And this is an example of the Bugey gravity compilation that Chris has done. And it shows the very different Bugey anomalies associated with the Lau Basin crust and the North Fiji Basin crust. Basically older, colder, thicker crust in the North Fiji Basin, and younger, hotter, thicker crust in the North Fiji Basin younger, hotter, thicker crust in the Lau Basin. What is the endowment of this region? This is the map that's on the floor here. Of course, there are hydrothermal vent fields that are of significance in the northern Lau Basin and the Niua vent field in the New Hebrides, in the northern New Hebrides, in the western Bismarck Sea in the Manus Basin. Those yellow stars are all being worked on by Melissa Anderson here at the University of Toronto and also by John Jameson now in Ottawa. But not only the marine endowment, but of course you've got the Emperor Gold Mine on Fiji, Bougainville, and the Latolum Gold Deposit on the island of Lihir, and probably many, many more we don't even know about because they're all underwater. This is the map that's on the floor here, and it's a compilation of work that's been done by about 12 different people, mostly master's students who mapped individual areas. I'll draw your attention to small little orange things that are located right here in Fiji and elsewhere. Those are the central volcanic complexes that Keaton was showing. So I'll give you a measure of the scale. We're looking at something like 5,000 kilometers from one end to the other, so that's Halifax to Vancouver, maybe a bit more. And a number of characteristics of interest. One is that the entire geometry and the history of the northern margin of the Indo-Australian plate is dictated by this big blue blob, which is the Ongtong Java Plateau. It collided with the Cretaceous arcs about 20 million years ago, collided at this particular location north of Lihir, or north of Lau Basin. And it's been a kind of a continuous, slow-moving car crash since then, resulting in incredible dissociation and dismemberment of these various basins, with new basins opening up all the way along that margin, including 3 of them here in Papua New Guinea, Woodlark, Solomon Sea, and the eastern Manus Basin. You'll see that there are quite a number of these hairpin turns. There's one here at the northern Lau Basin. There's another one here at Fiji, which was rotated through almost 120 degrees. This is phenomenal. In about 12 million years, the island or the platform of Fiji rotated 120 degrees, like spinning it on a dime. There's another hairpin turn here in the South Fiji Basin, and then another one here in the North Solomons, and another one here in New Britain. These are all places where slab tearing is occurring, or is likely occurring. We know of at least 2, one here in the northern Lau Basin, and another up here in the New Britain Trench. And you can put the Abitibi pretty much in any one of these basins for scale. They match almost identically, and so you can imagine how complex the complexity is shown here. You can imagine how complex that geology is. Here's a larger version of Chris's map, which shows that much of the slab tearing and much of the mantle flow into these back arc basins is always occurring where there is a dramatic juxtaposition of thin crust and thick crust. That's true in the northern Lau Basin, that's true in the Hunter Ridge down here, it's true in the South Solomon Sea, it's true in the northern Solomon Sea along the New Britain Trench. These are the locations where mantle is impinging on in the back arc basin. This is a Bouguer anomaly map. Chris is currently calculating or running his models for true crustal thickness. This is being done on the supercomputer clusters with the Digital Alliance of Canada, which is I hope it's not for profit organization that supplies this time. Chris calculates that he's used about 100 CPU years of time. And at 15 cents per core hour, if the bill comes, he keeps telling me the bill's not coming, but if it comes, it's going to be about $150,000. What I want to show, what you should look at if you come and look at the map, is how much we think we can unpack from this map. I mean, the entire length of the map is just a storybook of metallurgy. And the one area that we have done a lot of work in is in easternmost Papua New Guinea around the New Ireland Basin. There's the eastern Manus Basin, VMS deposits forming in the eastern Manus Basin, bizarre copper-gold arsenic deposits, which are Solwara 1, where the New Britain Arc is currently being rifted. And then just over on the other side, in the New Ireland Basin, the sedimentary basin is just about the size of the laser dot, the 60 million ounces of gold at Lihir. We've been continuing to work in this region, and we've now basically done our own transect, a metal earth type transect across the New Ireland into the New Ireland Basin right over Lihir. And the distance between the VMS deposits that are forming in the eastern Manus Basin and at Solwara 1 and at Lihir is literally identical to the driving distance from Timmins to Val-d'Or. And we continue to make discoveries here that we should have made 10 years ago because we've been going there on many, many cruises. We just published a paper in Nature Scientific Reports on the discovery of hydrothermal vents on the doorstep of the Latolin gold deposit, higher temperature hydrothermal vents. This should be some concern of the company, I would think, because these are an endemic ecosystem that probably ought not to be disturbed by the mining of 60 million ounces of gold. Here is another Bouguer anomaly map that's coming from Chris, and I hope to see it. I think the crustal thickness map is finished, right? Or is it still going? Another 50,000 bucks. Here's there's the Latolin gold deposit in that little white circle right there. There's the eastern Manus Basin with the black smoker deposits. That's the distance from Timmins to Val-d'Or. The location of the Latolin gold deposit is exactly above a slab tear or slab window in the downgoing Solomon Plate. So because of that hairpin turn, of which there are 7 of them on that map, because of that hairpin turn, you're opening up a window in the slab immediately below Lihir. As it turns out, some other work that we've done is to image this blue blob here, which is called the Lyra Trough. And this is, well, it's debated what it is, but one option is that it's a rifted margin of the Ongtong Java Plateau. And it's on a piece of the Pacific Plate with which is a subducting rift, also immediately under Lihir. So Lihir, 60 million ounces, is sitting on top of 2 slabs, 2 slab windows, all the way down to the mantle. So that's it for now. I wanted to simply, if you get a chance, come up and get down on your hands and knees and have a look at this map, because I've been working on it with everybody for a number of years now, and I can't believe the map, what we've come up with. We can do another one, 5,000 kilometers all the way through Indonesia. Think about Hijau and all the porphyry copper gold systems all the way through Sumatra and Burma and ultimately to India. That would, another 5,000 kilometers would get us there. So I don't know what, I mean, after you pay the computing bill. Anyway, that's it for me.